share my screen. Good day. Today is Tuesday, November 10. Okay, so this is still section what? 4.5. Optimization problems. Continue. Okay. One example today. What point on the parabola is closest to the point 4,4. Do you understand the problem? Can you read that? What point on the parabola is closest to the point 4,4? You see that, right? A nut.
Yeah, we can see it. Yeah.
We see it, yes.
Good. Can you draw the graph? So a parabola looks like what? That. What are the x-intercepts? What is a parabola? I haven't given you parabola yet. Parabola is y equals 4 minus x squared. Okay, that is the parabola. Sorry about that. So this is y equals 4 minus x squared. What are the x-intercepts?
I have a question.
Please.
Where'd you get the y equals 4x squared?
I'm giving that to you.
Oh, okay.
Okay, I'm giving that to you. So what are the points on the parabola? So this is the parabola. You see that? This is the parabola I'm drawing here. So what are the x-intercepts? -2 and 2, right? So this is the graph of parabola. Are you agree with me? Do you agree with me? Facing downward is negative x squared, and there's four units up. It's 4 minus x squared. Okay, so and what is the point 4,4? So here is the point 4,4, right? Now we have to find out the point on the parabola that is closest to the point 4,4. Do you see that? Do you understand the problem? So that point might be somewhere here. Right? That point xy might be there. Let's call that, we don't know that point. Let's call that point xy. We have to find the point on the parabola that is closest to the point 4,4. It looks like when you draw the parabola and plot the point 4,4, it looks like that point is somewhere there. Correct? Somewhere there. So So then we have to find, we don't know that point yet. So let's call that point, xy. Let's call that point, this question mark there. Is that the point? Okay, do you understand this? Do you understand our plan here?
Yeah.
Good. Okay, so then what are we maximizing or minimizing here? What is our, in other words, what is our objective function? Objective function. What is our objective function here? It is the, anybody? Let me see.
Would it be the parabola?
No. It's not the parabola. What are we maximizing or minimizing?
The line between the point 4, and parabola.
Yes, you meant to say the distance, right?
Yes, right.
Yes, it is the distance. Our optimization function is the distance.
Can you define the objective function?
Sure, we will. So, oh, you mean the definition of objective function?
Yeah, just in general.
Oh, okay. So it is the function that we plan to maximize or minimize. In
Okay.
other words, it is the function that we plan to optimize. So here we're finding out the point that is closest. How do you measure the closeness? It is the distance, isn't it? So I'm in Hammond. If you are in, so it is the distance, isn't it? It's the distance between the 2 points, right? Is that clear to you?
Right. Yeah, that makes sense.
Okay, good. So distance between the points xy and 4, isn't it? So what is the distance between the points xy and 4? You have to use the, let's call that distance be d. How do you find the distance between, you use the distance formula. Remember that if you have 2 points x1, y1, and somewhere here x2, y2, how do you find the distance?
Isn't it y2 minus?
No,
y2 minus y1
square. Let's put x1 first. I think that's what you're used to. x2 minus x1 is square plus y2 minus y square. There's the distance. Am I writing too small?
Yeah, I can't see that on the right, the formula.
You can't see, right? So it is x2 is square root of x2 minus x1 is squared plus y2 minus y1 is squared. Okay, I have to be. No, that's not Pythagorean theorem. That is the distance formula. Okay, Elizabeth, this is the distance formula. So it is then square root of, you can call xy is x and y1 1 point, and 4 is another point. Okay, so for the distance, x minus 4 square plus y minus 4 square. Do you all agree with me? Do you understand that? X minus 4 square plus y minus 4 square. Okay, but it's still in two variables, x and y, isn't it? It is still in two variables, x and y. So we have to write this in a single variable, let's say in x.
I have a question.
Mm-hmm.
How do you know which point is x1 and which point is x2?
Doesn't matter.
You can
pull, it doesn't matter. You get the same thing. You get the same thing because you are squaring, and even if you get negative, that will be positive. So you can put y minus, but you have to be consistent. Okay, if you call xy is x and y on, well, I think you understand that. So, but it doesn't matter. You can put 4 minus x squared plus 4 minus y squared also.
All right.
Okay, good. So then, so now write in terms of single variable, let's say x. How do you do that? Any? How do you do that?
We would use our y equals 4 minus x squared equation to.
Oh, very nice, very nice. So in the meantime, can you fold? Let's not fold this. Yes. So y is, you see that up parabola 4 minus x squared. Just put it there. Don't forget that another 4. Okay. 4x minus 4 is squared. What do you get? You should be getting x squared minus 8x plus 16 if you fold and simplify that, combine the like terms. Plus, here, negative 4, positive 4 gone. We have negative x squared squared. So that becomes what? Positive x to the 4, isn't it, guys? So it is in, if you want, you can write this in the descending power of x, meaning x to the power 4 plus x squared minus 8x plus 16. So this is our distance function in a single variable x. Question? Anyone okay with that? What is our interval of interest here? In other words, so what are the possible values of x and y we can assume here? Is there any restriction on us?
Maybe 0. Maybe 0 to infinity.
Well, you say x is 0, right? Can't we take x here on the left hand side? You see here, aren't we allowed to take, if you look at the graph, doesn't look like there, but is there any restriction? If there any, can we take the point here? You see the point that I am here? We can. At that point, x is negative, isn't it? Or can't we take x here? Here? That means x is positive and y is negative. So it looks like we can take x and y anywhere we want on the parabola. So that means our interval of interest is from negative infinity to positive. Do you agree with me? Just read the parabola. We can take anywhere we want. So what do you do from here? Well, you find out the critical point, right? Next is point. So you find out the derivative, d prime. How do you find derivative? Well, you can write this function derivative, I mean the distance function is the power of that and differentiate. Okay, use the chain rule. So d prime is what? You bring 1 up to the front, x to the power 4 plus x squared minus, not plus, minus 8x plus 16 to the power what? What do you get in the power? You know the chain rule, right? You have done that a lot.
Yeah.
Negative
Negative.
1/2 times, and
There.
what is left? Derivative of the inside function, right?
Right.
4x cubed plus 2x minus 8. Isn't it? 4x cubed plus 2x minus 8. Then set that equal to 0. How do you solve this for x? Well, before that, so you can, so we only have 2 in the denominator. You can bring this expression with negative exponent in the bottom. So that becomes x to the power 4 plus x squared minus 8x plus 16 to the power 1/2, which you can also write as the square root of x to the power 4 and so on. In the top, we have 4x cubed plus 2x minus 8 equal to 0. Now, how do you solve this for x? Well, multiply both sides by the denominator. Meaning, on the both sides here, multiply by 2x to the power 4 plus x squared minus 8x plus 16. 2x to the power 4 plus x squared minus 8x plus 16. So on the left hand side, the denominator is gone.
I have a question. I know what we did was just from the derivative, we put the first part of the function on the bottom as a denominator, but why do we put the first part instead of the second part or anything like that?
No. So here you see that we have negative exponent here.
Oh, okay.
Right? Yeah.
Okay.
So we just, yeah. Good? Understand that?
Yes.
Good. Then the left hand side, the denominator is gone. I mean, power 1/2 here. Okay. Right hand side is 0 times whatever is 0. We have that. Well, we can divide both sides by 2 or factor out 2. So it is just we have only what? 2x cubed plus x minus 4 equal to 0, right? How do you solve this for x? Can you factor? Not that easy, right? Not that easy. So it is, we can graph it. We can graph it. You can graph in your TI-84 calculator, but I cannot share the screen with you with TI-84. So what I do is, am I sharing my screen with you? That Desmond, do you see that?
Yeah.
Okay, so if you graph, so it's our function, our equation. So y equals 2x cubed plus x minus 4. Is that right? So we have only 1 0. We have only 1 0. And this is here, 1.128. We have Okay, 1.1. If you round to 2 decimal places, the x is what? 1.13. Do you all see that? The zero of that function, 1.128, round to 2 decimal places, so it is 1.13. Good, everybody?
Yes.
Good.
This is
Yeah, let's go back to, so we have then x equal to 1. What did we say? 1.13. But how do you know this number? This is a critical number. This is a critical number. Now, how do you know this number? What? How do you know this number? So this is a critical number, correct? How do you know this number minimizes the distance between the 0.44 and xy? Well, if you plot 1.33 here and choose some test points on the both sides of, now we are using the first derivative test here. Choose the test point. Which point do you want to choose here? You can choose 0, right? You can choose 2 test points. Now you plug in 0 for x in the derivative, or d prime, I should say. So d prime is 0. Now you can see that if you plug in 0 for x in the derivative, so this is your derivative. Okay, plug in 0 for x, you have what? -8 in the top, some positive number in the bottom. So looks like it is negative. Okay, and plug in 2 for x in the derivative, d prime again. The denominator of the derivative is positive anyway. You are taking square root, plug in 2 for x. In the top also, if you plug in 2 for x, you should get negative. So what does first derivative test tell us? Well, if the derivative changes its sign from negative to positive, it is something like this. On the left side of 1.13, derivative is negative. On the right side of 1.13, the critical number, derivative is negative, positive. So this is our critical number. Okay, critical number. Number. So what do we write here? You don't have to write, but this I'm writing this just for you, if you, in case you forget, because d prime changes its sign from negative to positive at x equal to 1.13, by the first derivative test. D has a local minimum at that point, 1.13. You understand that? That is the first derivative test. If the derivative changes from positive to negative, the function has local maximum at that critical number. If the derivative changes from negative to positive, the function has local minimum at that point. And we also know that if there is only on local max or local min, if there is only on local max, that has to be absolute max. If there's only on local min, that has to be absolute minimum. So the distance is minimum. In other words, closest when x equals to 1.13. Do you understand this? Or you need some time to figure out and process this in your mind?
I think that makes sense. Yeah.
It makes sense. Are we done it? What do you think?
No, now we need to find the y, right?
Exactly. Now we have to find the y. So we just find out, if you go back to the picture here, graph here. Oops. We just have x here, right? We have to find y too. How do you think we can find y? You know that our given equation, given function y equal to 4 minus x squared. 4 minus x is 1.13 squared. I have my calculator here. So it is 4 minus 1.13 squared. Oops. 4 minus 1.13 squared. 2 point. I have 2 point. If I round to 2 decimal places, it is 2.72. So it is the point. Don't leave your answer like that. You're finding out the point, so you have to put in order pair x, y. 2.72. Okay, understand this?
Yeah.
Okay, so well, guys, so I don't know, maybe I'll come back tomorrow. So if you have any questions from your homework, and let me know. Okay, we can work together. I love when you ask questions. So let's leave this here. Get this section here. If you don't have any further questions.
If we were gonna maximize it, what would we do?
So we minimize. We're asked to find the points. We're asked to find the point that is closest from the. We are asked to find the point on the parabola that is closest from the point 4,4. We just find out that. So this point is what? 1.33. 1.32. 32. No. 1.1. What did you write? 1.13, I think, right?
Yeah.
2.72. So it is, in fact, so it is 1.13 is somewhere here. Yeah, that's close. Okay. Now we start new section. Okay, we start new section. Something called linear approximations and differentials. Okay, linear approximations and differentials. If you want to write down that in your notebook, otherwise I'll send these slides to you. So you can find this. I don't know if you have an access, but the slides there is not complete. So I put a lot of, I put questions, I put a lot of graphs here. So I change everything there in the slides that you find in your MyLab Math. So what do we do here? at this two curves on the very top. Okay, very top. And on the left hand side, you have point P on the curve. On the right hand side, well, let's just focus on the left hand side. Let's just focus on the left hand side graph. Okay. Okay. Let's just focus on left hand side graph and the point P, and we draw. We pick a point P. We pick a point P here and draw a tangent line. Okay, we draw a tangent line at the point P. Okay, are you following me? Pick a point P, draw a tangent line at the point P. And what we do from there is zoom in several times. You zoom in once, you get this. You further zoom in, you get this. Then you further zoom in, further zoom in, further zoom in. As you successively enlarge the curve near P, what do you think it looks like? What do you think the curve, not the tangent line, what do you think the curve looks like at the point or around the point P, near the point P? Okay, you zoom in, you further zoom in, you further zoom in. As you successively zoom in near the point P, where we have both the curve and the tangent line, what would be the appearance of the curve near P?
It would approach to the actual tangent line.
Oh, very nice. That's very nice. That's very nice. So as you successively zoom in, the curve near P looks more and more like tangent line, right? So maybe I should write somewhere here. Do you all agree with me? Or your friend there? Okay, so maybe I should write here. Is you successively zoom in near the point P, the graph of the function. Okay, graph of the graph looks more and more like a tangent line at P. Okay, and so it is called the local linearity. Now, so the graph is not a linear function. It is not, the graph is not the straight line, right? But the tangent line is a linear function, isn't it? Y equal to mx plus p, it is a linear function. So the graph looks more and more like a linear function at the point P. Straight line, the graph looks more and more like a linear function, straight line. So we call that local linearity at the point P. At the point P. Now, so we are finding out the tangent line at the point P, means we can find the derivative of the function at the point P. Look at the graph on the right hand side. So we have the corner there. we have the corner there, or cost there, okay? We have the corner here. Now, so no matter how many times you zoom in, no matter how many times the zoom in, you cannot remove the corner. It still remains the same. The graph or the curve, the function near the point Q always remains the same, still the corner. On the right hand side, the more you zoom in, the graph near the point P appears to be like a tangent line at the point P. We call that local linearity. On the right hand side though, no matter how many times you zoom in, the graph still remains the same. Okay, now
I have a question.
please.
Is that the reason why magnification doesn't remove the corner at Q? Is that just because it's a point, not a slope or anything like that?
Yes, because the function is not, so here and on the right hand side, you cannot find the derivative of the function at the point Q. There's a curve. So if there is a corner, no derivative. If a function is not continuous, no derivative. If a function has vertical tangent line, no derivative, right? There's a corner, so no derivative there. Good. So we call that, you know what? So so now forget about the right hand side graph. Just focus on the left hand side graph. Okay. Now we can use this idea of the tangent line to the curve at P to approximate the value of the function near P. Do you understand what I mean? Now, suppose you have to find the value of the function at P. What does that mean? If your function is y equal to 2x squared minus 1, find f of 1. What do? You plug in 1 for x, right? So it's something like that. So suppose you have to find the value of the function at the point P. So instead of plugging that number for x in the original function, you can approximate that function using the tangent line. We call that linear approximation, and we call that linear approximation. So what's the whole point here? Well, if you draw, so if you find out the equation of tangent line to the graph at some point, then the value of the function can be approximated by that tangent line at that point P. Not anywhere, at that point P. And we call that linear approximation of the function at that point P. Look how this works, okay? So find the equation of tangent line. Find the equation of tangent line at that point P. So what is that? So you can start with y equal to y minus y1 equal to m times x minus x1. Okay, let's say x coordinate is a. What is y coordinate then? F of a. What is the slope? Or x, if x1 is a, y1 is f of a. What is m? Slope. Derivative of the function at the point A. So what is the equation of tangent line then? Y minus y1 is f of a equals, what is the slope? M. F prime a times x minus a, where a is given, this point here. Okay, so now if you solve this equation for y, what do you get? F of a plus f prime a times x minus a. So we call that you see here L for linear approximation. So it is nothing other than the equation of tangent line at the point P. So we started with something called linear approximation, which you may not have idea, but you see there, it is just, what is this then? It is just the equation of the tangent line at the point P. Do you understand this concept?
So we just figured out how we get the tangent line equation, that LX equation.
Yeah. So why do we call this LX? So what we said here is, so until now, so you learn how to find the equation of the tangent line. You did that in the previous chapter. So you know that, right? So you have the point. How do you find the slope? Slope is the derivative of the function at that point, f prime a. Right? So we have equation of the tangent line at the point a comma f of a. What we added here is that is not just the equation of the tangent line at the point P. If you zoom in that function, zoom in and more zoom in. If you zoom in that function is more and more looks like the tangent line at that point. So this f of a plus, yes, it came from the equation of the tangent line. But what that means also is that near that point a comma f of a, or if you call this point P, it is not just the equation of the tangent line, but it is also the approximation of the function at that point P. And this concept, this intuition is very important for you. So you should understand this. You might need this a lot going forward. I know most of you plan to do extreme measures, so you need this. Okay. Sometimes instead of when you find the value of the function, sometimes it is instead of putting the, let's say you have a function and find the value of the function at 1, find f of 1. Instead of doing that, sometimes it is helpful and more feasible to approximate the value of the function at that point using this linear approximation. And well, so I will send this to Carlos, and he will send that to you. And tomorrow we'll do some examples. We'll do some examples related to this one. Okay, so any question?